Welcome! Today, we'll tackle an interesting problem titled Problem number 564, Find the closest palindrome. In this challenge, we'll explore how to find the nearest palindrome for a given number. We'll approach it step by step, starting from the brute force method, and discuss its intuition and complexity. Let's dive in. In this problem, we are tasked with finding the closest integer to a given positive integer n that is a palindrome. A palindrome, as you may know, is a number that reads the same forwards and backwards, like 121 or 1221. However, the integer we return must not be equal to the input number itself. The concept of closest here is based on the absolute difference between the numbers. If there happens to be a tie, meaning two palindromes are equally close, we need to return the smaller of the two. Now, the input will be provided as a string n with a length between 1 and 18 characters, and it will not contain any leading zeros. Our output must also be a string that represents the closest palindrome to n. Let's look at some examples to clarify. For an input of n equals 123, the closest palindromes are 121 and 131. Here, 121 is closer to 123 because the absolute difference is 2, compared to 8 for 131. Therefore, the output is 121. In another example, where the input is n equals 1, the closest palindrome is 0. Even though the absolute difference is 1 in this case, we are explicitly told that the output cannot be the same as the input. Thus, the answer is 0. Now, let's consider a third example with the input n equals 99. The closest palindromes here are 88 and 101. Both have an absolute difference of 2 from 99. However, since we need to return the smaller integer in the case of a tie, the answer is 101. It's important to keep in mind that the input itself, n, can never be the output. We must find a different palindrome that satisfies the conditions. These examples also highlight the importance of carefully evaluating ties and ensuring the smallest valid result is returned. Finally, there are some additional points to consider. The result must always be a palindrome that is not equal to n, and we need to handle very large inputs, since n can be up to 18 digits long. Edge cases are particularly important in this problem. For example, think about cases like n equals 1, n equals 10, or even n equals 9999999999999999999. Additionally, remember that palindromes are symmetric, with the first half mirroring the second half. This property can help us construct potential candidates efficiently. Special cases include single-digit numbers, numbers that are already palindromes, and numbers close to powers of 10. Keeping these edge cases in mind will be crucial as we work on solving this problem. To solve the problem of finding the closest palindrome, we first considered a brute force approach. The intuition here is straightforward. We examine numbers incrementally below and above the given input n, checking each one to see if it is a palindrome. By doing this, we can identify the closest palindrome based on the absolute difference from n. The steps involve converting the input number to an integer, using two pointers, one to decrement below n and the other to increment above, and testing each candidate to determine if it is a palindrome. While this method guarantees that we find the closest palindrome, it has a major drawback: it is computationally expensive. For each candidate, we need to validate its palindromic property, and this process can require searching through a large range of numbers, especially for larger inputs. As a result, the time complexity is quite high, making the brute force approach inefficient in real-world scenarios. An optimized approach builds on the structure and properties of palindromes to reduce unnecessary computations. Instead of testing every possible number around n, we can directly generate palindromes by mirroring the first half of the input number to create symmetry. This significantly narrows down the candidates we need to evaluate. However, to ensure we don't miss the closest palindrome, we need to adjust these candidates, accounting for cases where the closest palindrome may be slightly smaller or larger than n. For example, special cases like powers of 10, such as 1000, require additional handling. The steps in this approach include identifying the first half of the input number, mirroring it to generate a symmetric candidate, and creating additional candidates by incrementing and decrementing the first half before mirroring. We also explicitly handle edge cases like numbers close to 10^k1 and 10^k+1. By comparing the absolute differences between n and these candidates, we can confidently return the closest palindrome. This optimized approach is not only elegant but also efficient, with a time complexity of O(n), where n is the length of the input string. This is because we only generate a fixed number of candidates, making the process much faster than the brute force alternative. One major advantage of this method is the significant reduction in the search space, as we focus only on a small, targeted set of potential palindromes. Additionally, by explicitly addressing edge cases, we ensure that the solution is robust and handles scenarios like trailing zeros or powers of 10 correctly. Given these benefits, the optimized approach is the clear choice for this problem. It combines efficiency with correctness, avoiding the pitfalls of the brute force method, which is impractical for larger inputs. When comparing the two approaches, the trade-offs become clear. The brute force method is exhaustive, systematically checking every possible candidate, but it is highly inefficient and computationally expensive, especially for large inputs. On the other hand, the optimized approach offers a much more efficient solution by leveraging the structural properties of palindromes. However, it does require careful handling of edge cases, such as numbers like 10, 100, or 999, which can complicate implementation. Despite these challenges, the optimized approach strikes a balance between accuracy and speed by constructing a limited set of candidates, ensuring both correctness and minimal computational overhead. In conclusion, the optimized strategy is the superior choice for this problem, as it delivers precise results without the inefficiencies of exhaustive search methods. In this problem, we're tasked with finding the closest palindrome number to a given integer n. A palindrome is a number that reads the same both forward and backward, like 121 or 1221. If two palindromes are equidistant from n, we choose the smaller one. To solve this, we can start with a brute force approach. First, we initialize two pointers, lower and higher, to n1 and n+1 respectively. These pointers will help us search for palindromes smaller and larger than n. As we iterate outward, we decrement lower and check if it's a palindrome, and simultaneously increment higher to check if it's a palindrome. This approach ensures we systematically explore potential candidates for the closest palindrome. To determine if a number is a palindrome, we need a helper function that converts the number to a string and compares it to its reverse. If they are the same, the number is a palindrome. This iterative process stops as soon as we find a valid palindrome on either side of n. If both lower and higher are palindromes at the same distance, we return the smaller one, which will always be lower. To implement the palindrome check function, we simply convert the number to a string, reverse the string, and compare it to the original. If the two strings match, the number is a palindrome. This makes the check straightforward and efficient. The stopping condition for our search is when we find at least one palindrome by decrementing lower or incrementing higher. If a tie arises, where both lower and higher are palindromes at the same distance, we return lower since it is smaller. We also need to consider edge cases. For example, if n is already a palindrome, we ignore it and search for the next closest palindrome. For very small values of n, like 0 or 1, we directly return the closest palindrome since the range of possible candidates is limited. Additionally, for extremely large values of n, we must ensure our algorithm can handle the constraints of integer limits without errors. Understanding these nuances helps us refine our approach. One key observation is that palindromes are symmetric, meaning their structure can guide us in designing more efficient checks or optimizations. Incrementing and decrementing around n ensures that we systematically search for the closest palindrome. While the brute force approach guarantees correctness, it can be optimized further. Instead of iterating blindly, we can leverage the mathematical properties of palindromes to generate candidates more efficiently. For instance, by mirroring the digits of n, we can construct potential palindrome numbers directly. This reduces unnecessary computations and narrows down the search space. However, the brute force method remains simple to implement and serves as a solid baseline. To track our progress during the search, we use two pointer variables, lower and higher, which represent numbers below and above n. Additionally, a helper function ensures that we can quickly check if a number is a palindrome by converting it to a string and comparing it to its reverse. Key operations in this algorithm include string conversion and comparison, both of which are efficient given the constraints. The complexity of reversing a string scales with the number of digits in the number, making this step manageable even for larger inputs. Overall, these data structures and operations form the backbone of our approach to solving the problem. The iterative search process involves incrementing and decrementing numbers around n to explore both smaller and larger candidates for the closest palindrome. This systematic exploration ensures that we identify the nearest palindrome efficiently. The time complexity of this search depends on two factors: the number of digits in the numbers we check and the distance to the closest palindrome. Checking if a number is a palindrome involves converting it to a string and reversing it, which takes k time, where k is the number of digits in the number. The overall complexity of the brute force search is d*k, where d is the distance from n to the nearest palindrome. To summarize this process, we can break it down with pseudocode. First, we define a function to check for palindromes by comparing a string to its reverse. Then, in the main function, we initialize lower and higher to n1 and n+1 respectively. We use a loop to decrement lower and increment higher until we find a palindrome. As soon as we encounter one, we return it. This ensures that the algorithm always finds the closest palindrome in an orderly fashion. Finally, let's analyze the complexity of this algorithm. The time complexity for the palindrome check is k per number, where k is the number of digits in the number. Since the brute force search involves checking numbers incrementally, the total time complexity becomes d*k, where d is the distance from n to the nearest palindrome. This complexity accounts for both the iterative search and the palindrome checks. On the other hand, the space complexity is k, for string conversion and storage during the palindrome check. However, the algorithm uses constant auxiliary space beyond this, making the overall space complexity 1. These efficiency considerations highlight the trade-offs of the brute force approach. While it's straightforward and guarantees correctness, its performance depends on the distance to the nearest palindrome. Optimizations, such as generating candidates by mirroring digits, can help reduce the search space and improve efficiency. By carefully balancing correctness and performance, this algorithm is well suited to handle a wide range of inputs, from small numbers to very large integers. Here, we start by defining a Python class called solution, which contains the method nearest palindromic. This method takes a string input, n, representing the number for which we need to find the nearest palindrome. Inside this method, we define a helper function called is_palindrome that checks if a given number, when converted to a string, reads the same forwards and backwards. Next, we convert the input string n into an integer and store it in a variable called number. This allows us to perform numerical operations later. We then handle a couple of edge cases for single-digit numbers. If the number is 10 or less, we return the largest number smaller than it, essentially, number -1. For example, if the input is 10, the output will be 9. Similarly, if the number is exactly 11, the nearest palindrome is 9. Following that, we prepare to generate potential candidate palindromes. We calculate the length of the input string and initialize a set called candidates to store these potential values. Two special cases are addressed here: the largest palindrome with fewer digits, which is created by subtracting 1 from 10 raised to the power of the number's length -1, and the smallest palindrome with more digits, created by adding 1 to 10 raised to the power of the number's length. Both of these are added to the candidates set. Next, we find the prefix of the input number by taking the first half, and possibly one additional digit for odd lengths, of the string representation of the number. Using this prefix, we generate new palindrome candidates by adjusting the prefix slightly, subtracting 1, leaving it unchanged, or adding 1 and then reconstructing possible palindromes based on these new prefixes. For each adjusted prefix, if the original number has an even length, we construct a candidate palindrome by appending the reverse of the entire prefix to itself. If the number has an odd length, we append the reverse of the prefix excluding its last digit. This ensures that the reconstructed number remains a valid palindrome. Each of these newly generated candidates is added to the candidates set. Once all potential palindrome candidates are identified, we remove the original number itself from the set, as it cannot be the closest palindrome. We then initialize variables to track the closest palindrome and the smallest difference between any candidate and the original number. Both are initially set to none and infinity, respectively. We iterate through the candidates set, calculating the absolute difference between each candidate and the original number. If this difference is smaller than the current minimum difference, or if the difference is the same but the candidate is numerically smaller than the current closest palindrome, we update the closest palindrome and the minimum difference. This ensures that we select the nearest palindrome, and in the case of ties, the numerically smaller one. Finally, after evaluating all candidates, the closest palindrome is converted back to a string and returned as the result of the function. This approach ensures we thoroughly explore all possible palindromes while efficiently identifying the closest one. Here, we begin by defining the Java implementation of the solution. The method nearest palindromic takes a string in as input, which represents the number for which we need to find the closest palindrome. First, we convert the input string into a long integer for easier numerical operations. We then handle some edge cases, such as single-digit numbers and the specific case of 11. For single-digit numbers, the closest palindrome is simply the previous number, so we return number 1. For 11, the closest smaller palindrome is 9. Next, we calculate the length of the input number and initialize a set to store possible palindrome candidates. We handle two special edge cases here, numbers like 999, which wrap to 1001 and 100, which wrap to 99. By adding these to the candidate set, we ensure that we account for palindromes with fewer or more digits than the input. After this, we extract the prefix of the number by taking the first half of the digits, which will be used to construct potential palindromes. A loop is then set up to generate palindromes by modifying the prefix by -1, 0, or +1. This ensures that we consider palindromes that are close to the original number. Now, we build the actual palindrome candidates based on the modified prefixes. If the length of the number is even, we simply mirror the prefix to create the palindrome. For odd lengths, we mirror all but the middle digit of the prefix. Each generated palindrome is then added to the candidate set as a long integer. To avoid comparing the number with itself, we explicitly remove the original number from the set of candidates. After this, we iterate through the candidates to find the closest palindrome. For each candidate, we calculate the absolute difference between it and the original number. If a candidate has a smaller difference than the current minimum or, in the case of a tie, is numerically smaller, we update the closest palindrome and the minimum difference. Once all candidates are evaluated, the closest palindrome is converted back to a string and returned as the result. This ensures that the function efficiently identifies the nearest palindrome to the input number by considering all relevant cases. In this example, we start with the input string 123. The first step is to parse the input. We convert the string 123 into an integer, resulting in the number 123. Next, we handle edge cases. Since the number is neither a single-digit number nor a special edge case like 11, we can move forward to the next steps in the process. Now we focus on generating candidate palindromes. The length of the input 123 is 3. We initialize our candidates with two fixed values, the largest number with one less digit, which is 99, and the smallest number with one more digit, which is 1001. These are derived using the formulas 10(3)1, -1 and 10(3)+1. Next, we determine the prefix of the number by taking the first half of the string, including the middle digit, if applicable. For 123, the prefix is 12. Using this prefix, we generate new palindromes by adjusting the prefix value with differences of -1, 0, and 1. Subtracting 1 gives a new prefix of 11, which produces the palindrome 111. Using the prefixes results in the palindrome 121, and adding 1 to the prefix gives 13, resulting in the palindrome 131. Combining these with our initial fixed candidates, we now have the set 99, 1001, 111, 121, 131. The original number 123 is then removed from the set, leaving the same set of candidates unchanged. The next step is to find the closest palindrome from our set of candidates. We initialize two variables, closest_palindrome as none and min_diff as infinity to track the closest value and its difference from the input. Iterating through the candidates, we first check 99. The difference between 99 and 123 is 24, so we update closest underscore palindrome to 99 and min underscore diff to 24. Next, we check 1001, where the difference is 878, which is much larger, so no update is made. Then, we check 111, where the difference is 12, which is smaller than the current min underscore diff, so we update closest underscore palindrome to 111 and min underscore diff to 12. For 121, the difference is 2, which is even smaller, so we update closest underscore palindrome to 121 and min underscore diff to 2. Lastly, for 131, the difference is 8, which is larger than our current min underscore diff, so no update is made. The closest palindrome to 123 is therefore 121, and this is returned as the final output. For the second example, the input is 1. After parsing, we convert the string 1 into the integer 1. Next, we handle edge cases. Since the number is less than or equal to 10, we immediately return the result of number 1, which is 0. Therefore, the output for this example is simply 0. In the third example, the input is 999. Parsing the input, we convert the string 999 into the integer 999. Moving to edge case handling, the number is not a single digit or special case, so we proceed. The length of 999 is 3, and we initialize candidates with the fixed values 99 and 1001. The prefix of 999 is determined to be 99. Using this prefix, we generate new palindromes. With a difference of -1, we get the new prefix 98 foot, creating the palindrome 989. With no change to the prefix, we get 999. Adding 1 to the prefix gives 100, resulting in the palindrome 10001. Combining these with the fixed candidates, our candidate set becomes 99, 1001, 989, 999, 10,001. Finally, we remove the original number 999 from the set of candidates, leaving 99, 1001, 989, 10,001. To find the closest palindrome, we initialize closest underscore palindrome as none and min underscore diff as infinity. Checking the candidates, 99 has a difference of 900, so we update closest underscore palindrome to 99 and min underscore diff to 900. For 1001, the difference is 2, so we update closest underscore palindrome to 1001 and min underscore diff to 2. Checking 989, the difference is 10, which is larger, so no update is made. Finally, for 10001, the difference is 9002, which is much larger, so no update is made. The closest palindrome to 999 is therefore 1001, which is returned as the final output. To analyze the time complexity of our solution, we start by breaking it into distinct steps. First, we calculate the length of the input string, which is straightforward and takes constant time, 1. Next, we generate two edge case candidates. The first candidate involves subtracting 1 from a power of 10, while the second involves adding 1 to a power of 10. Both these operations require calculating powers of 10, which take log n time, where n is the input number. Since these are fixed calculations for a given input length, they are considered constant operations for our analysis. Now, we move on to generating palindromes around the prefix of the input number. Extracting the prefix from the string involves slicing, which is proportional to the length of the input, or log n. For each of the three values of diff, specifically -1, 0, and 1, we calculate a new prefix and construct a corresponding palindrome by performing string manipulations like concatenation and reversal. Each of these operations is proportional to the length of the input, so this step also runs in log n. Since we repeat this process 3 times, the total complexity for palindrome generation is 3* log n, which simplifies to log n. Finally, we filter and find the closest palindrome by storing all candidates in a set and removing the input number. Determining the closest palindrome involves iterating over at most 5 candidates, comparing their differences with the input. Since this involves a constant number of comparisons and calculations, this step takes 1. Overall, the time complexity of the solution is dominated by the palindrome generation step, which is log n. Turning to space complexity, the analysis begins with input conversion. The input string is converted to an integer, which takes 1 space. Next, we consider the storage of palindrome candidates. These are stored in a set, and the maximum number of candidates is 5, 3 generated from prefix adjustments and 2 from edge cases. Each candidate requires space proportional to the number of digits in the input, or O, log n. Thus, storing these candidates takes O, 5 * log n, which simplifies to O, log n. Additionally, we use a few intermediate variables, such as prefix, new_prefix, and closest_palindrome. Since these are basic variables, they require constant space, or O1. The overall space complexity of the solution is dominated by the storage of the candidates, which is O, log n. To put this into perspective, we can compare the optimized solution with a naive approach. A brute force method would involve iterating over all integers less than and greater than the input, checking if each is a palindrome, and finding the closest one. This approach has a time complexity of O(n), where n is the input number, and a space complexity of O(1), as no additional data structures are used. In contrast, our optimized solution leverages mathematical properties to generate a small, fixed set of candidates, reducing the time complexity to O, log n, and the space complexity to O, log n. This makes it significantly faster and more space efficient for large inputs. In summary, the optimized solution is highly efficient, with both time and space complexities of O, log n, making it a clear improvement over the naive approach for this problem. When solving this problem, there are several common mistakes to watch out for. First, it's important to handle edge cases like single-digit numbers. These are inherently palindromes, so your solution should identify them immediately without performing unnecessary computations. Also, if the problem specifies that negative numbers are not palindromes, make sure to return early for such inputs. Ignoring this could lead to incorrect results or unnecessary complexity. Another common issue is with the palindrome check itself. For example, if you reverse a number or string to verify its symmetry, failing to restore the original value after modifications can cause errors later in the algorithm. Inefficiency is another pitfall to avoid. Using a brute force approach that checks numbers incrementally can be intuitive but may lead to performance issues, especially if you don't balance the search in both directions. Finally, remember to consider time complexity. Different approaches, such as brute force versus a mathematical method, have trade-offs. Overlooking these can result in solutions that don't scale well for larger inputs. Now, let's think about how to approach this problem in an interview setting. First, make sure you fully understand the problem requirements. For instance, clarify if the input includes negative numbers, 0, or special cases like single digits. Also, be mindful of constraints, such as the maximum input size. Optimizing for early exits is another effective strategy. For example, if you're searching for the closest palindrome to a given number, you can stop searching once you've found valid results in both directions. Pattern recognition is also key. Valid palindromes often follow repeated patterns or symmetry. For instance, a number like 12,321 mirrors perfectly around its center. Recognizing these patterns can help you reduce unnecessary checks. Lastly, be prepared to discuss trade-offs. In an interview, you might compare a brute force approach to a more optimized one, explaining why you would choose one based on input size or problem constraints. This demonstrates both problem-solving skills and an understanding of scalability. Additionally, this problem is closely related to a few other LeetCode problems that you might find helpful for practice. For example, LeetCode 9, palindrome number, focuses on checking whether a number is a palindrome. LeetCode 266, palindrome permutation, is about determining if a string can be rearranged into a palindrome. Another related problem is LeetCode 131, palindrome partitioning, where the goal is to partition a string into substrings that are all palindromes. Finally, LeetCode 214, shortest palindrome, challenges you to find the shortest palindrome by adding characters to the front of a string. These problems share concepts like palindrome detection, symmetry, and optimization strategies, so working through them can help you build a deeper understanding of the patterns and techniques involved. Finally, let's look at some alternative approaches to solving this problem. A brute force method involves incrementally checking numbers both lower and higher than the input to find the closest palindrome. While simple, this approach can become inefficient for large inputs due to its high time complexity. A mathematical approach, on the other hand, leverages the properties of numbers to directly generate palindrome candidates. For instance, you could mirror the first half of the number to create potential palindromes. This method is usually faster but requires careful implementation to handle edge cases. Another option is a string-based approach, where you convert the number to a string, manipulate it to generate palindrome candidates, and compare their differences from the input. This method can feel more intuitive, especially for beginners, but it might be slower for very large numbers due to the overhead of string operations. Each approach has its strengths and weaknesses, so the best choice depends on the specific constraints of the problem. Great job! We've summarized the key points of the problem and discussed important takeaways. Remember, practicing problems like this helps you improve both your logical thinking and efficiency in coding. Thank you for joining us, and don't forget to like and subscribe for more. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!